All right, so just one thing, maybe you may have seen or not may have seen, but I just added here one more document into the documentation. Okay, that you have before material table, geometric properties.
We can't see it.
Oh, what happened here?
Might be on the links.
Can you see now?
Yeah.
Okay, sorry for that. So what I was saying is that you go here to modules, you know, you have the section of documentation and lecture videos over here. So I guess it's, yeah, 20 to upload 21, 22. But basically, talking to the faculty teaching this course, I thought we're done. Personally, I think we're done, but they just want to make sure that also we kind of cover this. So since there's a lot of figures, I just decided to scan the document and go through with you. It's not the part of engineering that I like, it's what I call cooking engineering, but basically means go to this equation, find the recipe, and substitute without any much understanding. But we can look at it. Just going to go through it very quick. So you have it, and if you use it in advanced machine design, at least you know where to go and watch it. I want to say this is not really happening just with endurance stress, with any type of stress. Remember that we say that we calculate the principal stresses to be able to compare to yield values or ultimate stresses obtained from testing, the ASTM machine that want to do the testing in tension or compression. Okay, so obviously you can say that the experimental results may also depend on multiple factors, no? Okay, so you know you cannot say they are not perfect. So basically, that's what is over here. You know, like for example, for the endurance, while they do the testing on the laboratory, you might have different factors that come into play, as well as the material, the composition, the way of the manufacturing, the way that material is constructed. So, for example, I think we saw in one of them, for example, when we're talking about how to attach a gear to a shaft, we say that you could do like, you need to do a groove, but you can do the groove with a CNC machine or with a lead machine. I don't know if you know what exactly I'm talking about. But basically, depending on how you manufacture one part, can create a different stress concentration factors or another, no? Okay, so you also have the environment. It is going to be subjected to water, no salt, cold temperature, cold temperature. So, for example, if you have, let's say, I always say kind of some examples, but to have a car in the north where they put salt on the roads on the winter suffers a lot more than a car in Florida, no? Okay. So you start looking, so you do the design, let's say, of the brake or the chassis, you might want to take that into consideration, okay? So there's multiple stuff. And then at the end, it becomes ridiculous. That's what I like. Imagine what they tell you at the end. That the stress depends on 1, 2, 3, 4, 5, 6 factors. You know, that concentration factor times that value. So personally, I just give you one for the stress concentration factors. And if I need to do the design, personally, what I do is that all these ones, do you know what I do? Include them into my safety factor instead of each one of them. No, I don't know if that makes sense or not for you, but basically they want us to look at that. So imagine how many coefficients you have. K sub A for the surface condition, K sub B is for the size modification factors, K sub C is for the load modification factor, K sub D temperature modification factor, K sub E reliability factor, K sub L miscellaneous effects modification factor. I've never seen that one. S prime E rotary beam test specimen endurance, and S sub E endurance limit at critical location and machine part in the geometry. So obviously all these ones, sometimes they're going to be given to you, okay? But here you have it. I mean, I'll let you read these ones, you know. So this one is due to the factor, okay? If it's polished, if it's not polished, if it's smooth, not smooth, is it a scratch? Did somebody done the manufacturing remove an extra part of material? No, you might have to take that into consideration. So here we go. And obviously here you see factors for different type of machining, ground, machine called drawn, hot roll, as forged. So you need the table. So that's why I decided to do this online, because I think it's a waste of time to then do all the single tables in class, no? All right. So let me give you a quick example how to use the table. Size factor. This one is even worse. So size factor, you see, you have what I call cooking formulas. Depending on the factors that you need to use these coefficients over here, okay? That will give you for different diameters. For different diameters, you need to use a different equation. All right? Okay, once again, on every single one, they give you an example over here. Areas of common non-rotating structural shapes. So you see here, if you have something, they give you coefficients here, DE, there's an I-beam, a C-shaped beam. Loading factor, they give you 1.9485 is actual, 0.59 if it's in torsion, okay? Temperature factor, all right, that's another one. Temperature factor, you need to go to this table and you get it from all this stuff over here, all right? What are the other ones? All right, reliability factor. You need to use this equation. Who knows where it's coming from? Okay, most of it is coming from experimental. But since I cannot explain these ones, you have a table as well here for this one, miscellaneous effect factor, K sub G. You see that one can be due to corruption, or let's say, you know, they put over here like residual stresses. So let's say, I mean, you are not AE, but let's say on AE, sometimes, you know, like the landing gear, when they land almost on the aircraft carriers, since it's like a controlled crash, okay? What happens during a crash? I mean, if you go, well, even when you hit something, you're gonna have the structure is gonna absorb all the energy, and the energy is absorbed by what? Under which two force? Noise and heat. No? Okay. If you touch something that is subjected to a high stress, what happens? You first have the impact. I mean, somebody give you a slap, what do you have? First the noise, and then it probably gets hot in the area, no? And probably you get mad, no? But basically, if you want the energy of the impact, or if you want the landing, is transferred to the landing gear by noise and heat. So the heat is going to change also the material properties. So I think on a carrier, between each landing, they need to wait for the landing. The impact is so high, you need to wait at least whatever. I make it up, okay? But let's say 4 minutes so that the landing gears cools down again. All right, so it gets back to the property. So that could be residual stresses, because if you leave it over there without being cool, it's going to be residual stress. Obviously, same thing we were talking before, maybe about corruption. Okay, if you are up north or in the south, it might be different. Electrolyte plating. This one, I will guess, I think it's still a problem. But for example, if you have sailboats that were made of aluminum, what can happen due to the salt water? Corrode, but also it could be electrolyte, no? You have an electrical current going through it, creating corrosion. Electrolysis, okay? Whatever, megaspraying, cyclic frequency, ferrous corrosion. I mean, all kind of stuff you can think about it. And this stuff, we have done it indirectly, but this one is a little bit more picky, okay, that I say. It's just the stress concentration and notch sensitivity. So we have done a bunch of stress concentration, okay, both depend about a hole on the plate or on the manufacturing, on how you create the key, okay? But this gives you just an extra information. You see for the notch, you need to go to tables or a figure to find the radius, and this will give you the coefficient Q. And from the coefficient Q, you can find here the case of F, okay? And again, each one of them, it gives an example. So again, personally, I don't like to cover that because I think it's cooking, okay? It just comes from tables or from equations that you don't know where they're coming from. And personally, what I consider is that you only need to take into consideration the ones, for example, if you make a physical change to the structure like a hole, or you make a key for a gear or something, then yes, that's something physical that you need to take into consideration, no? But everything else that might be due to the machining, the material, I mean, the machine, let's say to the environment, the machining, what else? Some type of the design environment, I think is easier just to introduce all these coefficients into the safety factor. Okay, and that's why I don't really cover that much in detail. But in case you're going to use it next semester, I think it's important that at least you know that you heard about it, no? All right. So my idea now, like I told you, is just to come to class with different problems and working them with you. So let's do that. First, do you have any question about the assignment that is due today? Okay, I've seen some people that did some uploads and the ones I've seen look really good. Okay, to tell you the truth. So, all right, so Oh, another thing, I was thinking about imaging this as a printout, but then I thought it's better if you just copy it. Because that way you will learn it. When you sit, write it, and copy it, it's 3 times that you learn it. So like a summary to do all our problems, because some of you were asking me questions about exactly. I think this could be a helpful page for you for the equation for the different stresses, no? Since you have here, you know, like a little figure, this is the X, this is the Y, what is the Z, what would be the direction of the stress here? You see, this is the X, X and X, or this one would be the normal. And this will give you also the equation about the shear. Okay, so I mean, take a picture, you want to put your notes, other people can just copy it. And that way, there's no questions about the equations. Can use these ones. And I brought over here 2 different examples that I found. No, that's why I thought about it. I said, I want you to write it down. That way you learn it. Right before coming, I say,
ER over J instead of E for over.
I use, personally, I like the J more than the IP. Yes, I use J myself. Okay, let me know when you're done copying this. Like I mentioned, it's not out of mind putting this online, but if you have to write it down, you at least will learn it, no? Instead of just looking at it. Okay, so let's do now this problem together. Okay, so I'm just going to read it with you. They say a ski lift is supported by steel pipe, so it's this one over here, okay? With an outer and inner diameter of 60 and 52. So basically they kind of do here one figure, okay? Inside and outside diameter. Determine the stresses at point C on the front section of the pipe. So it looks like, it's about me. They do here the figure is right here, all right? And determine the principal stresses. So, I mean, on this one, they kind of give you a hint over here. So what is the first thing? You need to find the stresses at C, which would be at this location here where the cut is. What is the first step you need to do in our procedure? The first thing you did on the assignment.
Of course.
You need to basically, if you think about it, you kind of make a cut over here and find what are the forces being applied over here, no? Yes? So if you do it this way, so if you make the cut in this direction right now, you're gonna have probably an axial force due to this component here, no? One axial force, one shear force, and a bending force. So what about I give you 5 minutes? So it's 10:05, or it's going to be 10:05 until 10:10 to find the loading at this point at the cut, to find the axial force, the shear force, and the bending moment at this cut. And then I do it with you, okay? But I want you to have some critical thinking on your own. So I give you 5 minutes, starting now. Find the loading at the cut. All right, so I'm kind of doing a little figure over here. All right, so basically we start here, we'll just look at it. If we break this into a system this way and this way, they give us this angle here to be, let's say theta. We know theta is 45 degrees. So let's say this will be then theta. So this side over here will be what? Will be the y component, and this side over here will be the x component, no? So If you need to do this force over here, then Fx will be equal to what? So from figure, let's say here from left figure, what will you have? So let's say reduce summation of forces on the x equal to 0. This will give you what? So let's say we give you Fx over here as I specify here. Then what will you have over here? Minus what? W what? Sin theta. Okay, so actually I forgot this to sort this stuff. H. What is H on the problem?
It's the 0.4.6.
This one here?
I think so, because that's how it is.
Yeah, okay, ready. So basically, let's say and B. Okay, so let's say okay, B. All right. So you correctly. You have the information, okay. So basically, this will give you that Fx is equal to the weight times sin theta. Okay, and then we do the same thing for the y. This will give you what? Will give you y minus w cosine theta equal to 0. So Fy will be equal to w cos theta. So this will be step 1. I'm not being very good here, organized. So let's say here loading 1. Okay. And finally, what will you do? You can go and take the moments. The reason why I don't like this problem is that because generally you will look at what you will try to break this one into the two forces and find the perpendicular. Okay, which in this case you cannot do because they don't give you enough information, no? But actually it's the same as taking this force and find the perpendicular, or taking this force and find the perpendicular, as doing what? As just doing the weight. Then we need to find out the negative weight times what distance? Can we just call that distance? Okay, can I just call that distance by a letter? Can we call this a letter? I think that should be B, no, on the figure.
Yeah.
All right. B, and this looks like B and H, okay? And this is over here theta. Okay, so I like, I like symbolic as much as I can. So this will be then omega times B. So let's say we produce that as a clockwise, will be minus plus M equal to 0. M to be this one. So basically, this will give you M equal to the weight times B. Okay, so that's the reason why I don't like this problem, because this step was maybe not that straightforward. No? But any question about what we did? Does that make sense to you? Doesn't matter. Yes.
What is phi again?
B, just change here on the distance, is the distance between the force W where is applied and where the cut is on the figure. The important part is understanding what you're doing, no? You understand here? And this is probably the most complicated part, because if you don't have the correct loading, everything else is kind of useless, no? You do have the correct loading. Okay, now let's see what happened, okay? Now, even before we start, okay, if you look at this, at point A, the force, that point, what do you think is going to be? In general, it's going to be tension, compression. What should be the major stuff? What's going to happen to that element? The weight here, this one should be what? Tension or compression? What do you think? Okay. Let's find out. Okay, we want that. If you are pulling, it's not that you are compressing at the point. It looks like you are pulling, no? So initially, you must think that probably is going to be more intention than compression, no? Yeah, okay. So I'll give you an idea. You see, as I'm doing it with you. Okay, so I'll give you another 5 minutes. I mean, maybe we can do the next one together. So the next one you can do very quick will be maybe find the section properties, no? So step 2, I'll give you probably just about 2 minutes. 2. Then maybe do that one together. Section properties. So we might need, I don't know if we're going to need all of them, but we can do that figure here. Where we have the D outside. And the D inside. So maybe here's important to put what will be our coordinate system. So on the cut, what are we going to have on the cut? So let's say, but we make the cut. Let's say this will be the Y, X, Z. Then we need to make the Z in what direction? With the cut, this should be the kind of coordinate system, no? Yeah? X is along the length of the tube, no? So Y and Z will be the other one. So basically here, I don't know if we need it, but if you need to find the area, I'm not concerned about the values, but you can do the calculation. I won't be doing the calculations. Generally, area is what? Is pi square, but if you use the diameter, it will be what? Pi divided by 4 diameter squared. So we could say that this will be equal to 1 side over 4 d outside square minus the inside square. You can do the values. What else might we need? More inertia, but which axis? They're going to be the same, but we need to write down will be I, Z, Z, I, Y, Y. We're going to keep them just for the understanding of the equations, okay? And what was that one? 64 or 32? 64 per diameter, okay, 64, and then we'll have here D outside to the 4th minus D inside to the 4th. Again, after we're going to need all of them. We can do the calculations. And then at the end, the J, or what they call on that page, the problem of inertia will be just the same thing, but pi over 32 now. So go ahead and do the calculations. So you can give me those values. One thing, because here's, I want to do all this stuff in detail with you, okay? In very detail, so it's understanding. So maybe one thing here about M. This will be a moment on which axis? About which axis this will be rotating? What will be the M over here? If this is X, this is Y. You rotate about which axis? You know? Yeah. So let's put that over here and Z. That way we can do all the equations with a lot of detail. We put the IYY, IXX, and so on. I want to have that. So whenever you can, if you want, you can give me the values for the area, the moment of inertia. Remember, the best thing for you to study is to do the problems with me, that we all do the problems together in class, no? Calculations included. So what do you find for A?
7.037 times 10 to the -4 meters squared.
So 7 point something?
Yeah.
Okay, somebody else? I trust you, just don't want to double check with somebody. You can give everything in meters, it's not a problem. Meters, give me the result in meters or millimeters, but not centimeters squared, okay? I can live with that. Okay, so now that you have the values, the first step, I'm going to give you 10 minutes to do it. What should be the step? You need to find. So let's say step 3, you need to find stresses at point C.
Then we find the centroid here.
I mean, centroid, well, you know what the centroid is, no? It's right in the middle of the centroid.
No.
Oh, you said for the fuse?
Shears. Because we're gonna have a shear.
Yeah, correct. I need to give you those expressions. Yeah, let's find out what it was. Okay, this is a video, so I don't want to listen to video.
That's the inner diameter. So we have some gradient.
Let's do these first different axial stresses, bending stresses, shear stresses due to shear force, shear stresses due to torsion, and I give you, let's say, 10 minutes. All right, so let's do this one. So we said, first say the axial. So let's first look here. By A. So the axial stress in our structure, let's see, from the loading, what do we have? We have Fx, we plot over here is going in that direction from the cut, no? So what does that mean? If we show our cut over here, let's say we try making it sideways. See if I can show it sideways. Let's say we have this, so we have our force going this way, so this will mean that this will be what in tension, no? So what will you have? You have sigma x1, if you want to call it that way, will be equal to what? Fx divided by A. And if you do so, Fx was what? W. What you have for Fxw sine 45 divided by A. This will give you that the actual stress to be equal to, I mean, I have it here. If I can move this up. So it should give you 2.0096 10 to the 6. Is that what you got? 2.0096 10 to the 6 newtons meter squared. It should just be at the end some megapascals. I think here I gave you a hint, which is not too good. All right. So any question about this? You see, I do the equation, I do the figure, no? What is A over here? A is this one over here. Again, remember, this is the time to ask as many questions as you want. All right. Next, B. Find the bending stresses. So in this case, this would be again what? This should be a stress and a stress on the axial direction due to bending. So it will be equal to MC. So if I do here the figure, all right. Again, this is Y This is Z. Point C we say is over here. All right. So the equation should be equal to what? Z divided by what? Which one of this? This is bending. If you have the moment about C, this is bending on which axis? About the IZ, no? Yeah. And this should be then what? Y. Yeah, bending about this axis. So we look at this from here. So in this problem is pretty easy because what we have? What is Y of C? 0. And this is Y of C. So the bending stress, the actual bending stress due to bending is 0. Remember, this is the time to ask the questions. Okay, can I move to the next one? So 3. Now we need to look at the, so C. Shear stress due to Fy. So in this case, I'm going to write first Vy equal to Fy. And in this case, what you're going to have, you want to be accurate, you should have one over here, time of what? Yz, no, because it's in that plane, should be equal to Vy times the Q. And this will be going on which axis? I mean, here it doesn't matter really because they are the same value, but if you needed to put the letters, so this is YZ, we're looking at the force Vy now. Will be going through which one? What should we put over here? Okay, IZZ times T, no? Yeah, I mean, this is the equation straight. You see, I'm putting the indexes, everything. So over here from the page before, so in this equation, we know the Vy will be equal to what? W percent 45. Now the IZZ, we already have the value, but let me just put the T. What should be the T? What is the T? The T will be the thickness on this side plus the thickness on this side, no? So you write this should be D out is equal to D outside minus D inside. Okay, and finally the Q, I hope you copy that from before, but we can simplify this now. We can use the Q to be equal just to this equation, no? I'll show you before. So let's say it will be 2/3 outside to the Q minus R inside to the Q. And I guess that you know that D outside would just be R outside, sorry. R outside would just be D outside divided by 2. And R inside would just be D inside divided by 2, no? I can give you those values if you want. So V1, you know what it is. IZZ, we calculate. So you do this calculation. So numerical application. This gives you YZ equal to so you see how we have the 0, the Q is 6.2827 if you want to write it down, and this equal to 4.0057 10 to the 6. This is a Pascal. Again, I use Pascal is Newton meter square. Okay. So let's see if we can finish quick. D, shear stress due to torsion. So this is what? Tau YZ would be equal to what? T times R divided by J. But in this case, in this problem, there is no torque, no? So that means that basically the tau YZ due to torsion is 0. That was 1. Oh, we did, okay. Maybe I should have changed this one. Okay, so, and finally, what do we need to find? To find the principal stresses, which what is the equation? Sigma 1, 2 equal to what? Sigma x plus sigma, I mean, in this case, it's only sigma y, but it should be in our case, sigma x plus, no, it's y. Yeah, z divided by 2 plus minus sigma x minus sigma z divided by 2 square plus tau, what we are here, yz. Yz square. So basically we know here that where sigma x will be equal to what? What was the value we had initially? Will be equal to the top 2.0096 10 to the 6. Sigma z is 0, and the tau yz will be the one we just found, 4.0057 10 to the 6. So I'll go ahead and do the calculation on your side. I do it on my side. Okay, I do it live with you if you want, doesn't matter. Since I'm doing this in the forces and finally I will do here. I mean, you see that I use MATLAB, okay? So let's say will be equal to SG1 will be equal SGX plus SGZ divided by 2 plus SQRT of SGX minus SGZ divided by 2. Another parenthesis here, I guess. Square minus tau. Sorry, yeah, plus tau Z. I said, let me just write tau square, okay? Where in this case, we're gonna have SGX equal to what? SG X1 and tau equal to tau 1. Yeah, I forgot something here. Okay, did you do this calculation, guys? If I didn't do anything wrong. Okay, I don't know what is in the over here. SGC. SGC in our case is 0. So you find that the principal stress is 5.1346. .1346 10 to the 6 Pascal, sigma 2 equal to minus 3.125 10 to the 6 Pascals. And if you needed to find, I mean, we don't have time, but if you needed to find the maximum shear stress average, we just take this value here, no? Okay, any question, guys?